Welcome to a simple visual introduction to the core idea of calculus, focusing on how to measure the unmeasurable. We begin in a world of straight lines and simple shapes. For a right triangle, finding the area is straightforward using the simple formula. Area equals base times height divided by 2. For this example, with a base of 4 and height of 4, the area is 8 square units. But what happens when the boundaries aren't straight? Real-world problems often involve curves, like finding the area beneath a parabolic arch. Our simple geometric formulas no longer apply. The key idea of calculus is to break a complex problem into simple pieces we can solve. We approach the complex curve by dividing the area into a collection of simple shapes we understand, rectangles. We slice the area under the curve into a series of very thin vertical strips. Our first attempt is to approximate the area with 10 rectangles under the curve y equals x squared, from x equals 0 to x equals 2. Each rectangle has a width of 0.2 units. We calculate the approximate area by finding the area of each of the 10 rectangles and summing them up. The width is 0.2, and the height is x squared. The total approximate area is about 3.08. What if we made the rectangles infinitely thin? To get an exact answer, the gaps must disappear entirely. We imagine an infinite number of rectangles. The width of each rectangle, called dx, becomes almost 0. This moves us from a crude approximation to a perfect measurement. Congratulations, you now understand integration. This process of summing up an infinite number of infinitely thin parts is called integration. We use the integral symbol, an elongated s for sum, to represent this process. Thankfully, we don't have to add up infinite rectangles. Mathematicians developed the power formula, a shortcut to the exact answer for integrals of functions like x to the power of n. Let's solve our parabola problem with perfect precision. Applying the power formula to the integral of x squared from 0 to 2, we find the exact area to be 8 over 3, which is approximately 2.67. By comparing, our 10 rectangle approximation was 3.08. Using the power of integration, we achieved perfect precision, finding the exact area of 2.67. Now, let's test our new tool on the simple triangle we started with. The triangle is the area under the straight line y equals x, from x equals 0 to x equals 4. Can integration give us the answer we already know is correct? Integration confirms geometry. Applying the power formula to the integral of x dx, we get the exact same result, 8. The area calculated by calculus is a perfect match to the area calculated by geometry. Integration is more than a formula. It is a language for describing the world. This method is fundamental across science, engineering, and economics, allowing us to move from simple models to complex, real-world systems.